Welcome to this GCSE Maths revision video using fully worked examples of typical GCSE questions. This time, we are looking at a question that tests out your algebraic skills in using formulae, but also poses an instructive question about accuracy. I'm Mr. Lindsay, your tutor from mathstutor.uk.com. Let's look at what it's asking us. So, they've made a frustum by removing a small cone, so there's a small cone there, from a large cone, which is shown on the diagram. And they state that the frustum is made of glass and gives us the density of the glass, and that's 2.5 grams per centimetre cubed. And it asks us to work out the mass of the frustum. So we're looking at this figure here, made out from the large cone and removing the small cone. Let's get some paper. So where do we start on this? The best thing on these types of questions is to start with the actual question, which is, what is the mass of the frustum? So let's start by saying MF equals the mass of the frustum. And we've now got some representation of what we're trying to get to. Very important to write down any variables and give an explanation of it. Otherwise, the poor marker will be reading various letters and not knowing what they mean. So MF is the mass of the frustum. So the mass of the frustum has got to be equal to the mass of the whole large cone minus the mass of the small cone. And I think we've really got started now, but again, we've now listed two more letters or two more variables that we haven't described, so we must explain what those are. So we must say that ML equals the mass of the large cone, and that MS equals the mass of the small cone. So that's got us started, but of course we still have to calculate the mass of the large cone. Well, we've been given the density, and the density is 2.5 grams per centimetre cubed. And so therefore density must equal mass, because that's in grams, over volume, because that's in centimetre cubed. In this case, it's grams centimetre cubed. And we can rearrange this formula to get a formula for mass. And so therefore, we can say that mass equals density times volume. So we can now adjust our formula up here to include that additional information. So the mass of the frustum, we can now say, is the density, I'm going to make that the letter rho, which is the Greek letter, of the large cone, times the volume of the large cone, and again, we identify that we're using V for volume, minus the density of the small cone times the volume of the small cone. Because we've got the density of both the large and small cone, the density is given by the density of glass, because both the small cone and the large cone are made of glass. So therefore we now know the density and we can plug that into our formula. So we now have to work out the volume. Well, they've been very kind here, because they've told us that the volume of the cone is 1/3 times pi times the radius of the cone squared times the height of the cone. Well, we have most of that information. We certainly have the radius of the large cone, that equals 12 over 2, because that's the diameter, because that's given to us in the question, which equals 6 centimeters. We also have the height of the large cone. That's also given to us in the question, and that's 15 centimeters. The radius of the small cone is not given to us directly. We're going to have to calculate that one. But we are given, or we can calculate very easily, the height of the small cone, because that's going to be the height of the large cone minus the height of the frustum, which equals 15 minus 10, which equals 5 centimeters. So that leaves us with the radius of the small cone to calculate. Well, because the large cone and the small cone are similar shapes, the ratio of the heights is going to be the same as the ratio of the radii. So therefore, we can say categorically that the height of the small cone divided by the height of the large cone equals the radius of the small cone divided by the radius of the large cone. Unfortunately, we know a lot of this information, so therefore, plugging in the values that we have, we can say the height of the small cone, which is 5 centimeters, divided by the height of the large cone, which is 15 centimeters, equals the radius of the small cone, which we have yet to calculate, divided by the radius of the large cone, which is equal to 6 centimeters. So we now have to solve this equation for the radius of the small cone. Firstly, let's simplify. We know that both the top and the bottom are divisible by 5, so that equals 1 over 3. And we can multiply both sides of the equation by 6. So if I multiply that side of the equation by 6 and that side of the equation by 6, I then get 6 over 3 equals the radius of the small cone. So therefore, that equals 2 centimeters. We're now pretty much ready to apply our formula. So let's do just that. So let's go back to 1 again. The mass of the frustum equals the density of the large cone, which is the density of glass, and we're given that as 2.5 grams per centimeter cubed. And as long as we keep everything in grams and everything in centimeters, then that's going to be consistent, multiplied by the volume, and the volume is 1/3 times pi times the radius of the large cone. The radius of the large cone is 6, and that's squared, times the height of the large cone, which is 15. And we've then got to subtract the mass of the small cone, and the mass of the small cone is equal to the density of the small cone, which is still glass, so it's still 2.5, multiplied by 1/3, multiplied by pi, multiplied by the radius of the small cone squared. Well, we know the radius is 2, so that's 2 squared, multiplied by the height of the small cone. And the height of the small cone we have calculated here as 5 centimeters. We can see that the whole of this part is the same in both of these expressions. So therefore we can take that out of some brackets and minimize the amount of characters we have to put into our calculator. So we can rewrite this by, and it's called factorizing out that factor of 2.5 times 1/3 times pi. So we factorize that out and we say 2.5 times 1/3 times pi times 6 squared, with this 36, times 15, minus 2 squared, which is 4, times 5. And we can now plug that into our calculators. We type in 2.5 times pi divided by 3 times, and we put this in brackets because it's going to be multiplying this expression, 36 times 15 minus 4 times 5. And that gives us our answer on the right-hand side, 1,361.356817. So that equals 1,361, and let's say 0.36 to 2 decimal places. But the question then explicitly asks us to give our answer to the appropriate degree of accuracy, and that's a very interesting question. So what is the appropriate degree of accuracy? Is my 2 decimal places appropriate? And the only way that we can answer that point and decide what is an appropriate degree of accuracy is to look at the way that we're given the values. And if you look at each of the values that we've been given, so let's have a close look at these. Each one of these figures, 15, 10, 12, and 2.5, have been given to 2 significant figures. So therefore, an appropriate measure, or an appropriate level of accuracy, would be to 2 significant figures. The fact that all the values in the question are given to 2 significant figures. Therefore, the mass of the frustum is 1,400 grams to 2 significant figures. Please add any comments below so I know what works and what can be improved. And if you enjoyed this video, please subscribe to my channel and keep up with the content that matters to you. Till next time, goodbye.